Good day, grade 12s. Today you're with Mr. Papudi and we are doing mathematics. And the topic for today is differential calculus and is part of the topics that you'll be writing in paper 1 at the end of the year. And differential calculus accumulates to or contributes to about 35 marks of your paper 1. Remember, at the end of the year, you will be writing paper 1, which contributes about 150 marks. Remember, in the previous grade, you were taught how to calculate the gradient of a straight line. So this topic presents a new challenge, that is how to calculate the gradient of a curve. A curve can mean, for an example, a parabola or a cubic graph. Now, some of the subtopics that we'll be looking at under differential calculus, unit number 1, it is the limit. It's also a new term, so please make sure that you focus when we discuss that. So under unit 2, we'll be working with how to determine the derivative. Firstly, by first principle, all right? Secondly, firstly by first principle, secondly by the rules of differentiation. The topics that you see highlighted in blue, they are part of differential calculus, but for today's lesson, will be focused in Unit 1 and Unit 2, which is what you see on your screen at home now, all right? So let's get started with Unit 1, which talks about the limit, all right? A function, I'm reading from the board now, a function has a limit when it has almost identical values on either side of an undefined value, all right? So it means you would be having an undefined value, and you will see that there are values that are approaching that undefined value from the right and from the left. When that exists, it means now the limit exists. For an example, let's have a look at the next slide. Suppose you've got a given function y is equals to f of x, and when you substitute a certain value, in this case, I've represented it with a c, all right? When you substitute a certain value, if you can see here, on the blue bars, which are the x values, all right? You can see there's a value of c somewhere there, all right? Suppose when you substitute c into the function, it gives you an undefined value. There's no value of y, in other words, all right? So with the limit, where it comes in is, now let's say for an example, x values that are very close to the value of c, all right, your inputs. Let's say there are 1, I'm starting from the value of c going to the left, 1,001, 1,01, 1.1, 1.5, 2, 3. So they are increasing to the left, all right? And then on c, I've got on the right 0,999, 0,99, and towards the end 0,9. All right, so in blue, there are your x values, and underneath, next to the undefined value, you've got y values both on the right and on the left. Now, this is how it works. Focus here. Now, should you have x values that are written in blue approach the value of c from the left, all right? As you can see here, from 3 going to 2, 1.5, 1.1, we are actually decreasing towards the value of c. And from the right, 0,9, 0,99, we are actually decreasing towards the value of c. The very same way, the y values are behaving the very same way. You've got 1.9, they are increasing towards the undefined value. And also from the left, right, of the y values, from 4, 3, 2.5, 2.1, 2. They are decreasing towards it. So what you see is sort of, in terms of the x and the y values, these values seem to be converging towards the value of c and this undefined value. I'll just put f of c in inverted commas because it's an undefined value. Now, when this happens, we then say that as x values approach the value of c from the left and from the right, they approach, one specific value is approached. One specific value, that is the value of f of c, is also being approached from the left and from the right in terms of the y values. Now, that specific undefined, that specific unknown value, it is called the limit, all right? Now, it is expressed as the limit of that function when x approaches c, when x gets closer and closer to c, when x gets closer and closer to c, what you seem to be getting from the value is a specific unknown value. So maybe if I give you an example in the next slide, you will see, maybe you'll understand it better, but it's important that when you actually want to determine whether the limit exists or not, or what is the limit, it is important to look at the behavior around the undefined value, around that value that you do not know. Let's have a look at a specific example so that you can make sense of what I am saying. All right? Now, the example here says, determine the following limit. It says here, lim standing for limit. It says, limit of the function. The function you can see here, it is x squared minus 4 all over x minus 2. So you're going to determine the limit of this function as x approaches 2. Now, you will notice that should I substitute 2 into this function, you actually get 2 minus 2, which means it's a division by 0. So this function does not make sense because, you know, it's divided by 0. But if you actually have a look at the numerator, it is x squared minus 4, meaning I can factor it out to x minus 2 and x plus 2. And in that way, you will see that actually x minus 2 from the numerator cancels with x minus 2 at the bottom. And we are left with the limit as x approaches 0 of x plus 2. Now, in this case, we can do an easy job of just, you know, substituting x with the value of 2 because x is approaching 2, I mean to say. So as we substitute x with a 2, you will see that we actually stop to write the sign of the limit. So 2 plus 2 will in this case be 4. So it means now, what it means is the limit of this function as x approaches 2, the limit tends to be 4. All right? I'll show you a table just now of what I mean. Now, remember, in terms of x values, we are approaching 2. I am going to just select random values of x, for an example, because I want to see the behavior of the y values towards the undefined value, right? So on the right of 2, I've selected 2,0001, and then I've done 2,001. You will see a dot as I emphasize the specific x value that I want you to focus on. So towards the right is 2,01 and 2,1. On the left of 2, you get 1,1. And these are just the values that I thought of because I want to see the behavior of these y value towards the specific value of 2. Now, when I input 1,9, which is the value on the left here, into the function, it gives me 3,9. When I input 1,99 into the function, I get 3,99, all right? Towards, just like that until you get the one with 3 comma, and there are 4 nines there, all right? And on the right of the undefined value, all right, I get 4,001 and 4,001 and 4,01, just like that. So what you tend to see here as well is that I've got a specific undefined value, the value that I don't know, because when I substitute 2, which is the value of x, into the function, I get an undefined value, all right? So what you see here is that from the left, in terms of y values, 3,9, 3,99, 3,99, 3,999, these values seem to be increasing towards the undefined value. And on the right as well, 4,9, 4,01, 4,00, they seem to be decreasing towards this undefined value. When that happens, we say the limit exists because the left limit seem to be approaching 4, and then the right limit seem to be approaching 4. So it means in this case, the limit is 4. So you can almost approximate what this value is, what this undefined value is, by just looking at the table, because these values seem to be approaching towards 4. All right? All right, now let's look at the next subtopic in Unit 2, which is what you need to know. It is the derivative, all right? So I'm going to start with the definition because I need you to know how to define the term derivative, all right? Remember when we started, we talked about the fact that what you need to know in this topic that is different from what you did in the previous years. In the previous years, you used to do gradient of a straight line. So here we need to determine the gradient of a slope. So the derivative says a gradient or a slope. Remember, a gradient and a slope is the same meaning, all right? A gradient or a slope of a tangent at the point. That's the definition of a derivative. So we are going to be looking at two things. We are going to be looking at the gradient, and we are going to be looking at the derivative. Remember, the gradient, how we calculate the gradient is actually delta y over delta x, all right? A tangent, remember tangent, tangible. A tangent, it is a straight line that touches a specific shape only at one place. So it's a straight line. It will have properties of a straight line. It can be, or you will be representing it as in the form y is equals to mx plus c. So you can see there, I've highlighted m in red there to emphasize that should you look for the gradient as we did in the previous years, it was actually done in terms of change of y over a change of x. So the derivative, we will be looking at the gradient of a tangent at a specific point. Now, I just want to draw your attention to a straight line, which is what you did in grade 11, grade 10, and also other grades, grade 8 and 9. All right? Now, suppose you are given a function here, and the function is in blue, as you can see on your left-hand side of the green of your screen, and the function is given as 2x plus 1, all right? My emphasis on this is the gradient. Now, this function, it is written in the format y is equals to mx plus c, all right? So your gradient in this case, we can deduce it to the value of 2, all right? Because 2 is in place of m, all right? Now, should you select any 2 points on this line of the straight line, on this function, should you select any 2 points, this will always and always give you a gradient of 2, meaning all these points on this function are collinear, meaning all these points on this function give you a constant gradient. So here in this case, we are speaking about a constant gradient of the function of a straight line, which in this case is 2, as you can see highlighted in green. Now, suppose you were to do a tangent on this graph, all right? The tangent on this graph, the graph is y, f of x is equal to 2x plus 2. Suppose you were to do a tangent. The tangent, remember, it cannot cross. It will almost certainly touch the line at all points. So it means the tangent will become the line itself, all right? So since it becomes the line itself, so therefore it means now that the tangent would have the properties of the function that you see here, meaning it will share the same gradient as the function that you have there on the board. So the focus here, it is to determine the gradient. So the gradient of that tangent will be 2 in that case, all right? Now, remember the derivative, it is the gradient of the tangent, so therefore the derivative of f, which is the gradient of the tangent, will also be 2. So my point here is, you did a straight line, you can or you are able to do the gradient of a straight line, in this case being 2. Now, because of the tangent will be the line itself, that tangent will share the same gradient as the graph of f of x, all right? So our focus is on the gradient of a tangent. In this case, the gradient of the tangent is 2, so therefore the derivative is 2 because the derivative is the gradient of the tangent, okay? Let's do another example. Let's do another example on this, all right? Because I am aware that you are familiar with a straight line because you've done it in the previous grade. That's why I'm starting there, all right? Now, the next example says, g of x is equal to 2. All right? Now, this is a straight horizontal line. If I rewrite this formula in the form mx plus c, you'll see I've put a tick on your board, all right? So in place of m there is a 0 because 0 times x gives you 0, okay? So the gradient in that case is 0 for this given graph of y is equals to 2 or g of x is equals to 2, all right? Now, again, should you select any 2 points on this horizontal line, it will always give you the gradient of 0. As you can see demonstrated here on your screen, any change of y, any 2 points will always have values of y as 2. So any value of y will be 2 minus 2. So that will always in the numerator give you 0. So any values of x that you divide into that 0 will always give you a 0. So it means now, again, we are speaking about a constant gradient. We are speaking about a constant gradient. So therefore, you will notice that always when we speak about straight lines, they have a constant gradient. All right. Now, let's have a look at the effect of a tangent on this specific straight line. All right. Suppose I draw a tangent on this graph of y is equals to 2 or g of x is equals to 2. The tangent to the graph of g, right, I'm here now. Since the tangent at any point is the line itself, it means it will also share the gradient with that function of g, meaning the gradient will also be 0. Now, what I want to get to here, it is the derivative. Remember what we said about the derivative in the beginning? We said the derivative is the gradient of the tangent. So in this case, it means since the gradient of the tangent in this case is 0, so it means the derivative is 0. What I want to also introduce you to is the notation of a gradient. We are going to be dealing with this notation a lot. You can see there you've got g prime x, open bracket x closed equals to 0, all right? So once you see that sign, it means it's a sign for the derivative. It is a sign for the gradient at a specific point. But in this case, since all the points of a straight line have got a constant gradient, it is not quite distinctive, as you will see in the next few examples, all right? But be careful not to confuse the signs. Remember g of x, all right? Is it g of x, the sign g of x, all right? G of x and g of x there, and g prime x, right? And g minus 1x, they are not the same. This means this is a y value, all right, of the graph of g. And this one, this means it is a derivative at a point, means a derivative. If I may, my handwriting is not very nice there, all right, so I'll try and write it nicely. So it is, that means a derivative at the point, or the gradient at a point, and this one means the inverse, all right? The inverse. So these signs are not the same. So be careful about the sign between the letter G and the bracket, because it can give you different things, all right? Now let's go to the next slide so that you can see what I want to draw your attention to, because we are talking about the derivative, okay? Right, now it says, although the straight line function y is equals to mx plus c has or have a constant gradient, all right? We're speaking of m. Now, not all the graphs, however, not all the graphs, not all the functions have a constant gradient. For an example, other functions such as parabola and cubic graph actually do not have a constant gradient. In this case, we speak about the gradient at the point. Now, you will see in the next slide, the reason why I say not all the functions have an equal gradient. Let's have a look at this function that I have there. All right, it's a parabola, it's scripted in red. Now, if you have a look at the left-hand side of your green, drawn there in blue, All right, that's the tangent to that parabola. You can see that the blue tangent and the green tangent at the turning point of the function and the red tangent on the right-hand side of the graph, they are actually not having the same slope. So in this case, we cannot be speaking about a constant gradient because of the gradient on the left-hand side with the blue line is actually negative. The slope is negative. And at the turning point, you can see there, you see a straight line. It tells you that the gradient there is 0. And then on the right-hand side, you see a positive slope telling you that the gradient is positive. So in a parabola, not all the points have the same gradient because the curve keeps on changing and changing and changing. So since we cannot speak about a constant gradient like we did in a straight line, we say, I'm going to read from your screen on the right-hand side. The first bullet says, the gradient is not constant at different points, all right? Because the slope keeps changing. We only have a gradient at a specific point of the curve. Now we define the gradient of the curve of the function to be the gradient of the tangent to the curve at the point of contact, all right? So in order for us to determine the gradient, we'll have to be now looking at a specific point. Now, but it does not change. If you are looking for an average gradient is when you are given any 2 points on the curve, that is a parabola or any cubic function, as you will learn later. To calculate the average gradient is still not changing, just like you did in grade 11. It's still going to be the change of y over the change of x. All right? So now, since we are speaking about gradient at the point for a curve, how do we then now determine the gradient at a specific point? Now, this is what Isaac Newton and Leibniz did to determine the gradient at the point. Okay, their theory says, all right, suppose you've got 2 points on a curve, all right? That is point P and point Q. And those 2 points, they are on a curve, all right? And they've got a horizontal distance of delta x between them, all right? Now, let's try and sketch that so that you can have an idea of what I'm speaking about. Suppose you've got point P, and suppose you've got point Q, all right? And then the distance between these 2 points can be represented with delta x, or in most of the textbooks you will see that they actually use the letter h, right? The average gradient of line PQ, right? If I want to find the average gradient of line PQ, I can actually, in this case it will be a secant because it's cutting through the shape. I'm going to try and be as accurate as possible. Okay, so the line of PQ would look like that, the secant PQ. So using secant line PQ, as I've drawn in red, that gives you an idea of how I would do my average gradient should I be looking for the gradient of line PQ, all right? So I'll be using the point P, I'll be using the point Q, all right? Now, the distance between these two, the horizontal distance is delta x. Now, what we actually want is not the average gradient of line PQ. We actually are looking for the gradient at the point of P, okay? The gradient at the point P with a line touching once meaning this is a tangent at P. The tangent, okay? This is playing up a bit. So I'm going to erase that. I'm going to have, so this is a tangent at P because it's touching only once. So what we actually want to achieve is we would want the line PQ to behave like the tangent at P. So what they figured out is should you limit this, should you limit the distance, that is delta x, to approach 0, should you limit the distance between the 2 points to approach 0, you can actually calculate the average gradient of the 2 points. So what you will be doing is actually you are moving the point Q in such a way that it's so close to P, in such a way that the line PQ behaves like the tangent at P. So with those 2 points, you will be able to calculate the gradient at this specific point of P. Remember, you cannot substitute delta x, which is what you see at the bottom there. You cannot substitute it with 0 because this becomes undefined and then it doesn't make any sense. So for you to be able to calculate the gradient at the point, so this is the formula that you use, which is what you see here on your screen. Which is what you see here on your screen, and that formula can be simplified to the derivative of x, f prime x, equals to the limit as h approaches 0 of that function, right? Which is f of x plus h minus f of x all over h. So the h there represents the horizontal distance between any 2 points that you'll be looking at. Now this formula is called the first principle, all right? And we say that this formula of the first principle also has the following meaning. It also has a meaning, or it can be called the derivative of f at any point, or you can use it to calculate the gradient of f at any point, or you can use it to calculate the gradient of a tangent at any point. Remember, the gradient of the curve is equal to the gradient of the tangent at the point of contact only. All different points of a curve would always have different gradients. Okay, so this is the point that I brought to you earlier to say f at x represent the y value, all right, of the function at the given x value, but f prime x, there's an apostrophe there. That means it represents the derivative of f at any point, okay? So once we use the formula for the first principle, which is what you see here, once we use that and we use it to derive that whole process of deriving, it is called differentiation, okay? So this formula of the first principle can be used to answer any question should you be asked to derive using first principle. So derivative itself, it's got different kinds of notation. As you can see, the first one is f prime x, or you can call it the derivative of f with respect to x. That's the first one, right? The next one has y with a little apostrophe there at the top, so it's y prime. It's another notation to say that you are actually deriving. Another notation, it is dy dx, all right? Another one, it is df dx. Another one, it is dx, the derivative with respect to x. So all these signs that you see here on the left-hand side of the board, once you put them there, it means you are deriving. It means you are differentiating, right? Now, let's have a look at how we can apply the first principle formula, should you be asked to use it, to derive using this formula, all right? So the first thing that you need to do, is work out f of x plus h, all right, which is what you see here. What they've actually done is you substitute the value of x with x plus h. That's the first thing you do, all right? The f of x on the right-hand side actually represents the function that you're given. Be careful, before f of x, there's a negative sign there. So whatever that you have in terms of f of x has to always be in brackets so that you don't do any mistake, all right? So you don't start by substituting h with 0, because if you do that, then it renders this to be undefined, because any division by 0, it will mean this function is undefined, all right? So what you need to do now is the second step. I'm coming to here. Write down the formula f prime. That's what you need to do. That formula will be at the back of your formula sheet or your information sheet at the end of each and every test or examination. So don't panic if you can't remember it. It will always be there. You can copy and paste the formula into your answer sheet. Now, like I've said, you need to firstly work out f of x. F of x will be the function. F of x plus h, it means you'll be substituting x from the function with x plus h. Be careful with the exponent of x plus h as well as the signs. Simplify and remember to cancel out the denominator. What is the denominator? The denominator is the letter h. Remember, you cannot substitute it with 0 because it will render this to be undefined. Now, once you've done that, once you've cancelled h at the bottom, you can substitute h with 0. And at this point, you are no longer going to write the limit as h approaches 0. Now, let's have a look at the next example, and then I will perhaps show you how you can apply these steps, all right? Now, the first example says to determine f prime x. You stop there. F prime x, what is f prime x? F prime x, it is the derivative, all right? So we are actually, in this case, looking for the gradient at a point, all right? From what? First principles. Once they say you need to derive from first principles, the first thing that you need to do is run to the back of your question paper, information sheet, formula sheet, and what you do is to write down the formula. Okay, often there are marks to do this, all right, although it's just copy and paste, all right? So we are going to be deriving from first principle of what? Now look at my function. The function is f of x is equals to 2x plus 1, all right? Now, somebody already can tell me the answer looking at this function that I have. Remember what we said is always a straight line has the same gradient as a tangent. So this is a straight line 2x plus 1. I can tell it because it's in the format mx plus c. So that straight line would have the same gradient as that of the tangent, because should I attempt to draw any tangent on a straight line, that tangent will be the straight line itself, all right? So the gradient of a tangent in this case, you can tell there in place of m, it is 2. So that gradient of the tangent is 2, and already I can tell that the derivative in this case will be 2. So let's work it out and see if the answer concurs with what we are saying, all right? So we've got the formula there. So the first thing that we have to do, in the previous slide, we said that you need to work around getting f of x plus h, all right? So I've substituted, you can see that where there is x, all right? I put what? X plus h, all right? So where there is x, I put x plus h, all right? So I'm starting with x plus h. I got the formula already. So when I'm done getting x plus h, I am going to put it into the formula here, all right? Now, let's continue to simplify this. It says here f of x plus h is equals to 2x. The 2x, I get it by multiplying 2 times x, and I get 2h by multiplying 2 with a h. So at the end, I'm getting 2x plus h plus 1. All right, so that's the value of f of x. I'm going to leave it at that because I don't have any like terms on the right-hand side. So I'm going to take that, which is written in blue, f of x plus h. I am going to put it where I have a blue f of x plus h, all right? So written in red there is f of x. So where I see f of x, I'm simply going to substitute what I had been given in the question, okay? So the next step is I am going to do just that. So as you can see there, f of x plus h, I put 2x plus 2h plus 1, which I have on the left-hand side at the bottom. And in place of f of x, I'm going to substitute my function there, which is 2x plus 1, okay, in red, all right? So you can see that in the numerator, you can actually simplify that, multiply in the negative inside the bracket. So you are going to have minus 2x, and here you have minus 2x and minus 1, all right? So everything stays the same on the left-hand side at the top, right? Now, I also have some like terms at this moment on the numerator, in the numerator. So I can see there's 2x minus 2x. So I can subtract that because it gives me 0. They can cancel out. I also have plus 1 minus 1. They give me 0. So I'm left in the numerator with 2h. So I'm going to rewrite the limit when h approaches 0 of 2h all over h. So you can simplify it further by cancelling out the h. So your derivative, cancelling out the h. So f prime x, or the derivative using first principle for this function, will be an answer, will give you an answer of 2, which concurred with what we're saying, to say when you've got a straight line with a gradient of 2, right? That straight line will lie, should I draw a tangent on that straight line, it will have the same gradient as that of the function, and that gradient of the tangent is your derivative. So it's easy to do it with a straight line. Now let's have a look at what happens when you are using a curve. All right. Now the question says determine f prime x. Now what is f prime x? Again, is a derivative, the derivative of f. All right, the function f from first principles. Okay, first principles. First thing that you need to do is write down the formula of the first principle. Remember, you'll get it at the back of your question paper, or on your information sheet, or you call it your formula sheet. All right. Now this is the function now that we are working with at this stage. Okay. Now I'll go through with you the steps that we discussed earlier, so that I remind you about what you need to do. Remember, the first thing that we need to do is work out, first step, find what x plus h is, meaning we are going to substitute x plus h where we see x on the function. So we are going to work that separately. It makes our life quite very easily, instead of just substituting everything into the formula and getting complicated and probably making a mistake. So it's easier to work with it separately, and then when you substitute it into the formula, after you've written the formula, it makes everything quite nice and easy. All right. Now let's go through this specific sum. All right. Now it says here, we've written down the formula. All right. Now we've got f of x is equals to x minus 3x squared. All right. That's the function that we have. The first thing we need to do is to substitute x plus h. All right. So I've done that. I've substituted x plus h on the left-hand side. All right. And in place of x again there, I substituted x plus h. And in place of x there, I've substituted x plus h. Remember, I said in the steps that you need to be careful of the exponent of x plus h. In this case, on the right-hand side, we've got squared. So we need to simplify that, apply a little bit of algebra. So the 2 at the top there for the term minus 3x plus h, you can actually separate that into x plus h and x plus h. And you can multiply the two brackets of x plus h, and then you get x squared plus 2x h plus h squared. And you can multiply the 3 inside the bracket with the first term until h squared, and then you get minus 3x squared minus 6x minus 3h. All right. So remember, what we got here is what? What we got here is x plus h. All right. So we need to go and substitute it back into the formula that we have of f prime x. All right. Now let's do that. All right. We did that, and what you have on f of x here in red, it will be the formula that you were provided in the question. All right. So the next thing that you can do is to multiply the negative of f of x, the last bracket at the top in the numerator. You can multiply the negative inside the bracket there, so it will give you negative x and plus 3x squared. I left the rest on the left-hand side as it is because there is no like term. But at this stage, I see there are like terms. I have x and another x on second last term. So I can cancel that out. All right. So the next term, the next like term that I see in the numerator is minus 3x squared. I can cancel that out also. You will see that in the next step, everything that is left has the letter h in it. You see they have highlighted in purple to indicate h there. So all of these terms have got the letter h. Remember, you're not supposed to substitute h with 0 because it renders this undefined. So you can factor out h, and it will cancel out, leaving you with the limit as h approaches 0 of 1 minus 6x minus 3h. All right? So at this point, you have to go back and analyze. Okay, I'm working with the gradient at the point. The limit must approach 0. The limit of h when h approaches 0, meaning the term that you see there with a h, that h, if I substitute it with 0, all right, that term becomes 0 as h approaches 0, all right? So I will be left with the answer of 1 minus 6h. You will see that immediately when I analyze that term with an h to say, if h approaches 0, it means it will eventually become 0. If I substitute 0 there, I'm only left with 1 minus 6s, and I no longer write that notation, all right, of the limit. So that would be your answer. F prime x is equals to 1 minus 6s. That will be an equation that represents the gradient of any point for your function, right? Okay, now that we've went through that, I've showed you a couple of examples. We'll get to more examples at the later stage, but now I want us to focus on the next unit, which is determining the derivative by the rules of differentiation, all right? Remember, we started with the limit. We did determining the derivative using first principle, and now we are going to determine the derivative using the rules of differentiation. You are going to find this quite easy because it does not involve that long formula for first principle, all right? But it's got 3 rules that I've summed up that I want you to focus on that are quite very important. So rule number 1, let's get started. All right, rule number 1 is the constant rule, all right? Should you be given f of x is equals to c, that c represents a constant. The constant, I mean a number. Go back when we, at an earlier stage, we were referring to the function g of x is equals to 2, all right? So we analyze g of x is equals to 2, g of x is equals to 2, g of x is equals to 2. We actually found out that should you need to find the gradient for this, you can rewrite in the format mx plus c, and the gradient there will be 0, all right? So the gradient of this, because straight lines, they've got the gradient of this graph of g of x will be the same gradient as that of the tangent. The tangent would have this gradient of 2 as well, because should you draw a tangent on this line, they share the same, they will be drawn on top of each other, meaning they will share the same gradient. So that eventually became my derivative. So this rule number 1 actually speaks to what we did earlier, to say, should you derive any constant, that constant will always give you the derivative or the gradient of 0. All right, so the derivative of any constant, it will always be 0. The gradient of any function that is a straight line, that is a constant, it will give you a 0. Okay, let's have a look at this example. Here, again, I just changed g into an f. So you are given the function f of x is equal to 2, then you need to determine the derivative. You need to determine the derivative, the gradient, all right? So rule number 1 says derivative of any constant, it will be 0. If I calculate the gradient of any 2 points on the straight line, f of x is equals to 2, it will give me 0, all right? I think that's straightforward. Rule number 2 is the power rule. This one, very important. You need to focus a lot on this one, all right? Now, the first one, it says on the first line, it says you are given the function f of x is equals to ax to the exponent n. All right, so you've got this kind of a function. What you need to do is, to determine the derivative, you have to multiply the exponent with the numerical coefficient, or with the coefficient. The exponent was n, so I'm multiplying n with the coefficient, so it's a times n, and whatever that's is in the exponent, you take away 1. All right, so you take the exponent, multiply it with the coefficient, a times n, and whatever that was on your exponent, you have to remove or subtract 1. All right, now let's have a look at an example. I think this is straightforward as well. Now, the example says you are given, for an example, y is equals to 3x squared. Okay, now to determine the derivative of this, remember the derivative, where there is a derivative, we'll see by a sign. All right, so put in this sign, it shows us that you are actually starting to differentiate, you are deriving. All right, now what we had is you have to multiply the exponent with the coefficient. So in this case, I have to multiply the 3 with the 2. All right, and whatever that was in the exponent, that was 2, I have to subtract 1. Okay, so here I had 2, so in blue there, as you can see, I've subtracted 1. And 3 times 2, it will give me 6, and 2 minus 1, I will be left with 6x to the exponent 1. So it's quite pretty much easy as well. All right, it's shorter than using first principle. All right, let's have a look at the note on the right hand side. Very important. Please note that as you start to differentiate at any level, the derivative notation should be introduced so that we know that you are deriving. Okay, let's look at the third rule, which is the sum and difference rule. All right, now here what you have is you are, remember this sign of dx, this funny sign with the x as a subscript. Now you've got inside that, inside the bracket, you've got the function f of x and you've got the function g of x. So when you are deriving a polynomial, what you need to do is you can derive it per term. You can derive the first term, apply whatever, keep the same sign, and derive the second term. So you can derive it if you've got multiple terms or it's a polynomial, you can derive it by term. That's what this rule is saying. Now for an example, suppose you are given dx, right? 3 minus, in bracket 3 minus 7x plus 5x cubed. Okay. Now I am going to derive it by term. So I'm going to firstly derive the first term, which has the 3. So it's dx3 minus, I'm keeping the same sign, dx7x. All right, so I'm going to derive the second term, and keeping the same sign, plus, I am going to derive the last term. All right, so I've actually simply broken it down to different terms so that it becomes easier for me to work on. All right, now deriving the first term, this sign works quite in a funny way, because I've got the dx. When I start deriving, I'll have to remove the dx. All right, that's how it works. So immediately when you start to remove the dx, it actually indicates that you are starting to derive. So we are actually starting to derive at this stage because I am removing the dx sign. Right, so the derivative dx of 3, the derivative of any constant is a 0. So dx of 3 is 0. And dx of 7x, right? I'm going to apply the power rule there. So the exponent of x in this case is 1. It's not written as 1, right? It's just a dot there, but it's 1, all right? So it's going to be 1 times 7, as you see here in the next step. And whatever that was the exponent, that's what the power rule say. Whatever that was the exponent in this case is 1. You have to subtract 1, all right? So I've kept the same sign, as you can see there, still a plus. I am going to derive the last term using the power rule. So I am going to multiply the 3 with a 5. Whatever was the exponent is going to multiply with a coefficient. So I have 5 times 3, and whatever was in my exponent, I'm going to subtract 1. So it's 3 minus 1. All right. So what I have in the next step is the 0 falls away. All right. So I've got 7 times 1, which is 7, minus multiply that with a negative. So I've got negative 7. All right. So in the next term, I've got 5 times 3. All right. So that will give me 15 times, and then a positive there will give me a positive 15, and 3 minus 1, I get 2 there. So the exponent for x will be 2. So it's quite pretty much simple. What this rule is saying, you are going to be using power rule, but you just break it down in smaller bits so that it's easier for you to work on. All right. Now let's work on some examples. All right. Example number 1. I know you are afraid of square roots. Most of my learners are, so I hope here you are a bit relaxed because we are going to be working with a lot of them. Right? Now, the first sign that you see here, example says determine dp dt. Again, dp dt. That is a sign for derivative. So it means here again we have to derive. What are we deriving? We are deriving p, this is the function that we are given. All right? That's what we need to derive. P is equals to x over t4 plus, this is 3, the cube root of t squared. All right? So if you are looking for the derivative, you can use rule number 1, 2, and 3, at the same time. But what I want to draw your attention to, firstly, that you need to do is the sign for the derivative. It says here dp. All right? So if there's a p in the numerator, it means now whatever the function that you're working with, p must be the subject of the formula. All right? And then t at the bottom there, it means whatever on your function that you have, t must be isolated on the right hand side. P must be one side, t must be one side, and it must not be in a denominator, it must not be under any root. So we'll have to remove any root should there be that. Okay, so I just simply rewrote the function that I'm given, which is p is equals to 8 over t4 plus cube root of t squared. Remember the sign says derive p in terms of t, meaning p must be the subject. We have that at this stage. And t dt, we are deriving with respect to t, so t must be removed under any root, and it must be removed under any, if it's a denominator, for an example. So I'm going to start with the first term, which is 8 over t4. So I'm going to remove the t4 under the denominator and rewrite it as 8 to the 8t to the exponent minus 4. Remember, it was positive. When it goes upwards, it's a negative. I can do that. I can remove the t to the numerator because it's just only one term. That's very important. Now I can apply the exponential rule. Here, remember the exponential rule says if you've got nth root of any term there, this can be simplified to am over n. All right. So as you can see there, the 3, which was outside the root, now goes to the denominator of my exponent. All right. Now in the next step, I am ready to derive because I don't have t under any root. I don't have t in the denominator. All right. So I can derive. Remember, when you start to derive, what do you need to do? You need to indicate that by using the sign. Right. So the sign here, they said we need to derive by p in terms of t. So let's do that. Let's introduce the sign when we start to derive dp dt. All right. Using power rule. Remember what the power rule said? The power rule said if you've got x to any exponent, this can be derived to a times n x, whatever that you have in the exponent, you have to take away 1. All right. Now, this is what I'm going to do. I'm going to multiply -4 with 8, all right? And whatever that was in my exponent, I'm going to subtract 1, as you can see there in blue. So I'm going to use the sum rule, derive term by term, all right? So I'm going to keep the sign plus. The exponent of t in the second term was 2/3, so I'm going to multiply that with the coefficient of t. In this case, it was 1, so it's 1 times 2/3. Whatever that was in my exponent, I am going to subtract 1, all right? Now, from there, in the next step, I am going to have 8 times -4, that is -32, and in the exponent there of t, -4 minus 1, that will give me -5, plus 1 times 2/3, that is 2/3, and in the exponent 2/3 minus 1, I have -1/3. Very important, make sure that at all times your exponents should be left as positive. So it means now I've got a problem here because the exponent for the first term of t is -5, and in the next one is -1/3. So I can rewrite them as positive by actually taking t to the exponent -5 into the denominator. And when I do that, it changes the sign to positive. And on the right-hand side, that can be simplified to the cube root of t, all right? All right, let's have a look at the next example. But before we do that, this is what I was emphasizing, that as p is differentiated with respect to t, meaning dp dt, p must be the subject of the equation and t should be in the numerator and always in exponential form, all right? The derivative symbol, dp dt, is written when we start to differentiate. Okay, let's have a look at the second example. Again, we know that we have to do the derivative because of the sign, p apostrophe x into x. So that sign tells us that we actually need to find the gradient, the expression for the gradient at a point, or the derivative of p in this case with respect to x. Now, the function that I'm given is p of x is equal to x cubed plus 8 all over x plus 2. Now with this one, be very careful. I cannot remove the x and immediately take it to the numerator, or I cannot isolate the 2 and take it to the numerator because it's actually 2 terms in the denominator, all right? So what you learned in grade 10, remember the sum and difference of 2 cubes? Here, I can factorize the numerator into x plus 2 and x cubed minus 2x plus 4 all over x plus 2, and then the x plus 2 cancels out, and I have p of x is equals to x squared minus 2x plus 4. Take note, I have not written any notation for the derivative on x. I have not written any apostrophe between the letter p and the x because I have not derived. I have not started to derive. I'm just simply simplifying what I have on the right hand side. That's why I kept it as px, all right? You only do the sign when you are ready to derive, all right? So let's derive because x is no longer in the denominator, all right? So when we derive using the power rule, as you see on the right hand side, that tends to be 2x minus 2. I am deriving. How do I know that? That this is the derivative by the sign that I have on the left hand side there, all right? Now let's have a look at the next example. The next example says that you need to determine the derivative of y is equals to open bracket root x minus x squared close bracket 2 squared, all right? All squared, right? So remember what we said. We said that x should not be under any root, all right? Or it should not be under any fraction, right? In this case, because this is all squared, we can start by simplifying this bracket before we can derive this expression. So let's start to do that. Let's actually simplify the expression. You see here in the next step, I have rewritten the root x in the form 1 over x because a root without a number, it means there's a 2 there and there's a 1 there, and using, sorry, let's just get this on a new board. It means here that should you have any root of x, all right, if there's no number written, it means the number is 2, and the exponent there is not written, it means it's 1. So this can be written in exponential form, and it will be 1, and the 2 will go into the denominator there, all right? Now, that's what I have there. I've written 2 brackets because that was all squared. If there was a 3, I would have to write 3 brackets there, all right? So I've got 2 brackets there. I can multiply out the brackets, and then it will give me the first term. Remember, when you multiply, you have got to add the exponent. X to the exponent of a half times x to the exponent of a half. Half plus half, it gives me 1. Hence, you see that that is actually just x, because if it's to the exponent 1, there's no need to write the exponent. So I've multiplied also x with x squared, x to the power of a half with x squared. So that gave me x to the power 5 over 2. I do it with the next term as well. Gives me x to the power of a half, and also the last term. So it gives me positive x. When you add the exponents, they give you x to the power of 4. All right. So you can actually see there I've got like terms there. All right, because they are both to the same power. So I can add them because they are 2 negatives. So I keep the common sign. So it's x minus 2x to the exponent 5 over 2 plus x to the power of 4. I'm ready to differentiate at this level because x is no longer under any root or under any fraction. So what I can do is I can actually start to derive. I'm going to use the power rule combined with the sum rule, differentiating each and every term one at a time. How do I know I'm deriving? Remember y to prime, right? Now, so I have the exponent of x was 1. So I'm going to multiply that 1 with the 1 that was there, which is 1 times 1. So whatever I have in the exponent, I'm going to take away 1. If you forgot the power rule, you can see it on the right-hand side of your screen, minus what I had in the exponent, 5 over 2, times the numerical coefficient, in this case is 2, and I am going to take away 1 from the exponent, and I'm going to do the same thing with the last term, all right? So my answer here will be 1 times 1. Obviously, it gives me 1, and 1 minus 1 for the exponent in the first term. For the exponent of x, 1 minus 1 means it's 0. Any number to the exponent or any term to the exponent 0, that will eventually become 1, right? So as you can see there in the middle there, I've got in the exponent, I've got 5 over 2 minus 1. That gives me 3 over 2. And the last term, I've got, I'm keeping the sign. 4 times 1 is 4. 4 minus 1, it gives me the exponent of 3. So I don't like to have fractions in the exponent, so I'm going to use the rule that you see on the right-hand side there. See, you can't see it clearly there, so I'm just going to rewrite it here. So it was supposed to be a to the power n over m. So that can be written into a set form, which gives you root m of a to the exponent n. Okay, so I am going to rewrite my answer. X to the power of 0 becomes 1, all right? And then I am going to write that x in set form. So you're going to have that. There's no need to write the 2 if you want. It's just, you can just write 5 root x cubed plus 4x to the power of 3, all right? So we've looked at quite a number of examples on limit, on differentiating or determining the derivative using the first principle, and also determining the derivative using the rules, all right? So I just, in the next slide, would like to combine all of them. So you see the kind of questions that you can get for these different sections, okay? So these are just mixed questions based on the aspects that we dealt with, or the concepts that we dealt with today. So the first question here, it says, provided you are given f of x is equals to 3 minus x squared, okay? So you need to determine f prime x, meaning the derivative from first principle. Remember, the first principle deals with that long formula that we learned, that we also said, if you can't remember, it's okay. You can find that at the back of your question paper or your information sheet, okay? So the very first one, because specifically they say we need to derive by first principle, we absolutely need to use that. You cannot use the rules if they say use the first principle, unless you're not going to get any marks, all right? Now on 1.2, they say you need to determine dy over dx if they've given you two questions there, all right? Remember, our explanation says look at the sign, all right? The sign says dy dx, so it means whatever example that you're going to be working with, you need to make y the subject. In this case, it's much more easier because they've worked it out for you. So in the next example, at 1.2.2, we would have to make y the subject because y is not the subject in this case, all right? So dy dx, determine dy dx means y is at the top, dy, it means y must be the subject, and I am deriving with respect to x, right? And at 1.3, which is kind of a new question, I thought I would bring it into the mix. It says here, you need to determine the value of x where the gradient of the tangent to f at x, open bracket x minus 5 all squared. You can see there, we've got a parabola there. So the gradient of the tangent to this function, that gradient of the tangent is minus 8. So remember also earlier on we talked about the gradient of a tangent. We said that the gradient of the tangent is equal to the gradient of the function at the point. So there's a formula that we used to say the gradient of a tangent, it is equal to the gradient of a curve at a specific point. So this is what we had in the notes, okay? So I would like you to remember that expression as you deal with this, because it works with the gradient of the tangent simultaneously with the derivative of that function. Okay, so the last one here, it's just another question again on first principles. Remember, once they ask you to determine the derivative using first principles, you have to use the formula, right? So we are going to work with that. I just thought I would introduce that because it, as you can see there, it's not similar to whatever that we have done because there is a fraction, right? So now let's look at the first one and do all of them. First one says, determine the derivative from first principle. First principle formula, f prime x is equal to the limit when h approaches 0 of f of x plus h minus f of x all over h, all right? So remember again, at this stage, you cannot substitute h by 0 because this will be undefined, all right? So the first thing that you need to do is to work out f of x plus h. That's what we said earlier. Now, how do you get f of x plus h? Where you see x from the given function, which is 3 minus x squared, where you see x, you are going to be substituting with x plus h, all right? So we can simplify it further. It gives us f of x plus h is equals to 3 minus, there's an all squared there, meaning you can factor this out and multiply it out. So it gives you when x squared plus 2x h plus h squared, as you can see there. And then when I multiply the negative inside the bracket, you will get minus 3 minus x squared minus 2xh minus h squared. So you have to be quite very careful when you are working with negative, because once you go wrong here, it might affect how your answer looks at the later stage. Okay, so this is what I have on the left hand side. Is only fx plus h. Okay, it's only this guy that you see here. All right, so I simply just need to substitute this into the formula there. Remember, f of x in red, f of x is what you are given here. I've highlighted that in red as well. So where I see f of x, I'm simply just going to be substituting that there. Let's have a look at the next step. So where there's f of x plus h, I put what we got on the left hand side, which is 3 minus x squared minus 2xh minus h squared minus f of x. In place of f of x, I put 3 minus x squared, which is the function that is given to me. All right, so that is all over h. All right. Right, so I can simplify this further, all right, by multiplying the negative inside the bracket. So this negative here that you see next to the arrows, when I multiply that into the bracket, I get negative 3, and the negative with the negative is plus x. I didn't change anything here on the left hand side because there are no like terms. There's a number 3 and x squared. There's no other x squared term in the previous step here. If you have a look here, I haven't done anything on the left hand side because there wasn't any x squared term or 2x or h squared. Okay, I just copy and paste it from what we got on the left hand side. Okay, but at this step there are like terms, because I can see there's a 3 and a minus 3, right? So they cancel out. 3 minus 3, that becomes 0, and I also have minus x squared plus x squared. So the two, when you add them, they give you a 0. So again, all the terms that are left at this step, all of them would have a h. As you can see, the h I've highlighted in green, meaning you can factor it out, and once you do that, you can have 2x minus h, right? And the h's on the outside can be simplified. All right, so this h will cancel this h, leaving you with minus 2x minus h. All right, so at this point, you can work around the last term, which is negative h, because h is approaching 0. It means now h is ultimately becoming 0. So you are going to have your answer, which is the derivative of f of x. The gradient of this is the expression that represents any gradient at any point of this function that you provided. So it will be equal to minus 2x, right? Now let's have a look at the next question that we had. This question says we need to determine the dy dx. Who must be the subject? Y must be the subject. Y must be the subject of the formula. In this case, the formula is okay, so we are deriving with respect to x. Somebody looking at this equation might be thinking, oh, okay, now we've got a pi. What should we do? Remember, a pi is a constant, all right? So we are not going to be looking much at it. We are going to be biased to the x because we are deriving in terms of x, all right? So firstly, I am going to convert the set form into an exponential form. So the exponent in the denominator of the 2 there, the exponent for x inside the root was 1, right? It was 1 set form, this was 1. So remember, this can be, again, I'm writing this because of, I know some of you might have, forgot the exponential rule, changing a set into an exponent. So the 3 goes into the denominator of the exponent of x, so it becomes a third minus pi x, all right? Now in the next step, I'm going to take the x to the power of 1 over 3 to the numerator. I can do that from this step because it's only one term at the bottom. So the exponent of x to the power 1 over 3 in this case is positive, so when it goes to the numerator, it becomes negative. Okay, so this is what I have. X is not in the denominator, X is not under any set, so it means now at this stage I am ready to derive. I am deriving dy dx. Remember, when you are ready to derive, what do you need to do? You need to put the sign to show that you are actually starting to differentiate. Now, the sign dy dx is equal to power rule. Again, I'm going to remind you about the power rule. The power rule says if you are having any function a x to the power of n, the derivative f prime x at a point, that would be equal to, I am going to multiply that a with the exponent, and whatever that was in the exponent, I am going to take away 1. So applying the sum and difference rule means you have the advantage of working with each term one at a time. All right. Now, I have in the expression I had here, I had y is equals to 2x to the exponent minus 1 over 3. So it means I'm going to take the exponent of 3x, which is negative a third, and multiply it with the 2. All right. And whatever that was in the exponent, I am going to subtract 1. All right. Minus the pi there, it's a constant. It's like having a 2 or a 3 or whatever number you can think of. All right. But we know pi is quite a very long number. It's 3,14. It's quite a very long number. So you treat it like you would treat any constant or any number. So the exponent of x in this case is 1. So you're going to multiply that exponent of x, which is 1, with the number or with the pi, and you are going to remove or subtract 1 from the exponent of x, which was 1. So in the next step, all right, you can keep on writing dy dx, all right, which is equal to, you just simply apply algebra here. It's just 2 times negative 1 over 3, so that answer will be negative 2 over 3 x to the power minus a third minus 1, that gives you negative 4 over 3 minus pi times 1, that is pi, and x to the exponent 1 minus 1, that gives you a 0. 1 minus 1, it gives you a 0. Remember, anything to the exponent of a 0, in this case, only x is to the exponent 0, so it's the only one that will become 1, all right? So the other one, the first term, which is to the negative 4 over 3. Remember, I'm trying to run away from any fraction or negative exponents in my solution. So I'm going to rewrite that as positive. In the denominator, move the x to the denominator, and it will change the sign to a positive. And I can also change this exponent that you see there in the denominator of x to a set form. So I'm going to have negative 2 over 3 cube root of x to the power 4 minus a pi, because 1 times pi, the answer would be pi. All right. So we've done quite a lot to this stage, but let's keep on going because we still have some time left. Let's have a look at the next example. Again, in the next example, we are determining the derivative dy dx. Remember, when you're deriving dy dx, y must be the subject with respect to x. So in this case, as you can see, y is not yet the subject in the equation that is provided. So we need to make y the subject of the equation. So you can start by factoring out y. All right. So that would become y is equal to x minus 1. Y in bracket x minus 1, it's equal to x squared minus 1. All right, so I can make y the subject by dividing with x minus 1. Automatically on the right hand side I had a difference of two squares that can be factored to x minus 1, x plus 1. And you see there that you can cancel out x minus 1, right? You can cancel out x minus 1, leaving you with only y is equals to x plus 1. No x in the denominator, no x under a set. So determining dy dx becomes easier from this step. Now remember, when we are starting to derive, we need to introduce the notation. So here I just wrote 1 because as you know, should I derive one term at a time, this x would be 1 minus 1 and 1 times 1, and on the right hand side I had 1. This is deriving. Okay, I'm just simplifying this so that some of you can see what I'm doing. So when I derive 1, it's going to be 0. So here I'm actually going to have this. 1 times 1 is 1, x to the power of 1 minus 1 is 0. So that's going to be 1 times 1, which eventually gives me 1. The other term on the right hand side just falls away because it is 0. So the answer in the end, the derivative of this equation will then become 1. Right? Let's have a look at the new question that I like so much because it's linked with the next chapter that you are going to be doing. All right, here it says, read it very carefully. Determine the value of x. All right, so here the question is, you need to find the value of x. So we need to find x when where the gradient of what? Of the tangent. So we are speaking of the gradient of the tangent. Okay. Where the gradient of the tangent to f at x, you can see is a parabola there, because if you multiply out x minus 5 all squared, it will give you an L squared. So that function is a curve, it's a parabola. Now, we need to determine the value of x where the gradient of the tangent to this function is equal to minus 8. Gradient of the tangent, what did we say about the gradient of the tangent? The relationship of that to a curve, we said that the gradient of the tangent at a specific point is equal to, I'm just going to rewrite this nicely. All right. Okay, right. So the gradient of the tangent is equal to, this means is the gradient of the function f. All right. So the point here would be at the point where x is equals to a. How do I know that? Have a look at my formula. It's called a. All right. So whatever the value of x there is at that point, you'll then need to substitute it in the expression of the derivative. So what this is telling us is that the gradient of the tangent is equal to the gradient of the curve, very important, at the point of contact. Now, what is the point of contact? The point of contact in this case is at the point of contact. All right. So the point of contact in this case is x is equal to a. All right. Now let's have a look at how this works out quickly, because I'm running out of time. So the gradient of the tangent is given as minus 8. And step number 2, we have a look at f of x, right? Now f of x is equals to x minus 5 all squared. So we are going to let the derivative of f to be equal to the gradient of the tangent that is provided, all right? Now the gradient of the tangent, that is minus 8, the derivative in this case is 2x minus 10. So the value of x, you'll have to get it from this expression, because you have allowed the gradient of the tangent to be equal to the gradient of the curve. All right? So the aspects that we dealt with today, I just want to quickly rush off to the end of this slide. If we have enough time, we'll come back. All right. All right. The aspects that we dealt with today is, firstly, we dealt with the limit. All right. We dealt with the concept of the limit, which is quite very new. We said the limit can only exist if you've got the y values that are approaching the undefined value, and it can be expressed as the limit of f of x when x approaches c. That value, that y value that you will get there, it is called the limit. Right? Now, what is a derivative? Derivative, we said it is a gradient or a slope of a tangent at the point. Then there are different notations that you can use, as you can see there, to express the derivative. And what I just showed you now, it is the gradient of the curve is equals to the gradient of the tangent at the point of contact. Point of contact in this case, it is when x is equals to a. So you can allow that to happen, because a parabola or a curve will not have a constant gradient through all the points. So this is how you can determine the gradient of the tangent at the point. And we also dealt with differentiation by first principle. There's very long formula that we mentioned that you can actually find it in or at the back of your question paper during a test or an exam. Same thing, you will find it there, or you should find it there. Your teacher should have it there in case you don't remember it. Now also that we dealt with the rules of differentiation, and very important is the power rule there. All right, that you need to multiply the exponent with the coefficient which was there, and whatever the exponent was, you need to subtract 1. Remember, very importantly, should they ask you to derive, to find the derivative using first principle, you are forced to use this equation, right? But if they say just say derive, you can use any other rule from the 3 that we learned today. All right? And I would like to leave you with this message for today, that it is in your hands to create a better world for all who live in it. That is a quote from Nelson Mandela. I hope you are all well at home and safe during these unfortunate circumstances of COVID-19, and I hope that you have relaxed enough so that you can do even more examples from your textbooks, since now we have went through some of the aspects of differential calculus. It's got quite a lot of weight. It weighs about 35 marks from your paper 1, so take it quite very serious, and I hope you return back to school very soon. I hope so. I hope the president releases that statement very soon. So please take care. All right? Thank you.